In this video, we're going to review all of functions and relations. To start with, I'm going to answer a student question around how to apply transformations to circular functions. Then from there, we're going to go through the Cambridge Review chapter. Enjoy. So for this one, it's going to be a revision of pretty much all of the functions and relations style stuff. To start with, there is a student question we'll go through, which is going to be a quick revision of how we can apply a set of transformations, x dash, y dash, to circular functions specifically. The key thing here is that there's actually no real difference between applying transformations to circular functions versus any other kind of function. There will be a slight nuance in how this one in particular will be handled, not because of how you apply transformations, but simply because of the list of possibilities you have in the multi-choice. So as far as how we actually apply these transformations, this x dash, y dash stuff, first step is always to rearrange back in terms of x and y. Ultimately, we're trying to apply a transformation to a function. So to put it into that function, we first need to have it in terms of x and y. So we start out with our two possibilities there. X dash is 2x, and we have y dash is a third y. From there, we're just going to rearrange to get x and y on its own, like I suggested. X dash over 2 equals x, 3 y dash equals y. So we've now got our y and our x on their own. Now we can sub it into the function that we were provided. So the function that we were provided was y equals 3 sine of 2 bracket x plus pi over 4. This works just like you normally would for any substitution. Every y is going to be replaced with 3y, every x is going to be replaced with x over 2. So this becomes 3y equals 3 sine 2. X is now x over 2, and the plus pi over 4 is still going to be there. Now, we could see a pretty quick simplification. Dividing both sides by 3 would cancel those out. So we could do that, giving us our circular function y equals all of that. Now, if we look on our answer sheet, there actually isn't any A, B, C, D, or E. None of those match up to this. So we're going to have to do a little bit more simplification. Any thoughts on how we might simplify this further?
Since the inner isn't like sine x, do we substitute it with something?
So you're saying like replace all the brackets with like a u substitution?
Yeah.
Okay, so if I did that, it would be something like y equals sine of u. That'd replace the entire brackets where u equals 2 bracket x over 2 plus pi over 4.
Well, we're not solving, so maybe
Yeah.
that's not correct.
So I like the idea in that you're seeing the connection between how you might solve it in this case. So it's good that you're able to pull that up, but just not for this particular case. We're looking for a specific way to rearrange this such that it looks like one of the matches on our answer sheet. Now, that doesn't mean that substitution is bad, because some trig identities can be used more effectively if you do a little substitution. Like, for example, this isn't the case, but if this was a negative on this 2 here, then what you could use is the identity that negative sine x is equal to sine negative x, where x is just something in brackets. So in this case, if we made like all of this a u, then yeah, we could flip that around using some trig identity stuff. Now, we don't have exactly that here, but we do have something similar that we'll eventually be using. So that's not to say substitution is bad, just not the quite right time for it. So any other ideas as far as simplifying what's in there?
Chris, could we distribute the two?
Yeah, sounds like a good idea to me. Y equals sine. So 2 goes through there to make it just x, and then 2 pi on 4 becomes pi on 2. That looks much simpler. Do we have a match? Not quite. So we can see all the possibilities there. We've got some sine, we've got some cos, we've got some plus pi's, and we've got some minus pi over 2's in there. It can pay to look back and forth between what you have and what's available in the A through E answers. That might inform what kind of simplification you use. So from here, this one won't be any more algebra per se. It'll be trig identity stuff. So this will be a bit of revision. Who remembers their trig identities? What this could be potentially rearranged to look like? And I guess a reminder, this would be a tech active because it is, well, I mean, not would, it is a tech active. And so even if you don't remember your trig identities, there is a way you could CAS bash it out. So I'm open to hearing a suggestion around that as well.
Chris, since like the plus pi over two is like like a shift in the graph, right?
Correct? Yep.
Wouldn't that mean that this graph is effectively just a cos graph?
Yeah, it's exactly what it means. So what do you think the answer is going to be based on what you just discussed?
D.
Yeah, D, precisely. So there's this identity that says sine x plus pi over 2 is just the same thing as cos x. That's a trig identity thing, or if you think about it in terms of the graph, like you suggested there, perfectly fine as well. Now, for those who either don't remember their trig identities or don't want to, I did mention there was a way to bash it out on the CAS. So if you think about least amount of effort, because this is a tech active thing and you should be trying to basically solve these as fast as possible, one of the things you can do at this stage is define your function. Well, maybe not even define it, just have it in the CAS, some way, shape, or form that we have. So after our full simplification, we had sine of x plus pi over 2. Now, what you can just do is go line by line, A, B, C, D, E, and just equate this function to what's in there. If it says true, congratulations, you found a match. If it says false or anything other than true, you would just move on to the next thing. So I could say h of x is equal to sine of x plus pi. Pretty unlikely, and sure enough, not going to happen. You go to the next one. H of x is sine of x pi, minus pi over 2. So again, pretty unlikely, right? Minus pi on 2. Not going to happen. You would keep going and going and going until you make it equal to cos, in which case, I bloody well hope it's going to say it. It'll say true. And so when you see that true, you know that the left-hand side is equal to the right-hand side without even really thinking too hard. As long as you know how to sub in your x dash y dash, you now have the match that you're looking for. So, in summary, you still need to know how to do your x dash y dash stuff. That never changes as far as transformations. A little bit of algebra doesn't hurt, but even here, before you distribute that too, you could still put it into the CAS if you wanted to. As far as a tech-free solution, you'd be using this identity. If you're using a CAS, it would just be CAS bashing out. If there's anything I need to clarify, let me know. Otherwise, we shall go on with the remainder of the revision for the rest of functions and relations. So I'll pause for a second. All right, let's move on then. So we're just going to go through chapter 8 here. It's going to be a mix mash of basically everything. So question 1. Polynomial has a specific remainder when divided by some linear. Find the possible values of a. I'll pause for a moment while you guys have a think about that. whenever you're given a question that you may or may not understand, a good thing to look for is all the numerical information that's in there. So things like the polynomial, obviously going to be important. Remainder being -4, that's probably going to be important. This linear, also probably going to be important. And then obviously at this point it's like, okay, we know we've got to figure out our possible values of A. So one of the things that can be helpful is to try and figure out how can we get a starting equation based on the numerical information that we're given. What information do you think would be important for creating at least a equation to start off with?
We're gonna have a remainder of 4 of -4 after
Yeah.
division.
Yeah, correct. Remainder of -4. So what kind of concepts come to mind when you think of remainders of polynomials? Any particular equations?
The remainder theorem.
Yeah, for sure. So, remainder theorem. Remainder theorem is just f of -b over a is equal to the remainder, whatever that remainder happens to be, and f is the polynomial. So I guess in this case, if we were to rewrite this specific to this question, we would want to have our p out the front. Now, as for what a and b are, those come from a generic linear, ax plus b, right? So the coefficient on the x goes on the bottom, the b value goes up here and is made negative. So we know based on remainder theorem that p of -b over a must therefore be equal to -4. That's our starting equation, or at least almost our starting equation. We've got to figure out these terms in here. Any ideas what would become that fraction? Or at least how we might create it?
Would it be -5a over 6?
b -5a over 6. Let's see, where would that come from? Where did the 5a and the 6 come from?
The
Oh,
first and second
okay.
terms.
You're looking at these two, yeah. Not quite. So the ax plus b that creates the fraction that's in here, this is the linear that you're dividing by. So that's a stand-in for that. So with that in mind, we're comparing that to this x minus a here. That's what we're dividing by in this case, x minus a. And so the coefficient on the x, that's going to be 1, meaning our a value here is going to be 1 on the handwritten bit. So denominator 1. And then our b value is going to be -a, and then negative makes positive. So what you end up with is capital P of, so divide by 1 is just nothing, and then, well, it's just capital P of a, I guess, in that case. So, maybe that's a bit hard to see how that comes about. So I'll do the negative from before. There was the -a from that linear, and we're dividing by the coefficient of 1. So that's where that all came from. And then all we're doing is, we've got a double negative there, and dividing by 1. That's why it's P of A. Do I need to clarify that at all? Okay. So, P of A was that. So what we have is this equation that says P of A is going to be equal to -4. P of A equals -4. Well, the good news is we actually have our P of X equation. So we know P of X is the cubic. All we're going to do is replace all those X's with A's. So we're going to have 6A all cubed, not all cubed, sorry, just the X, plus 5A times A again, and then minus 12A equals -4. And that's just coming straight from subbing in X into every spot on P of X. This is just a polynomial, and our goal is to try and solve it. So we'll do a bit of simplification first. 6a cubed plus 5a squared minus 12a plus 4 equals 0. Yeah, that's about it really for now. So we have an equation with only one variable in it, which does mean that we're pretty much able to solve it directly from here. No further information from the question required. The question now becomes, how do we solve polynomials?
And like trial and error some like possible values.
Yeah, trial and error, unfortunately, using the factor theorem. Do you remember how to create your list of trial and error values?
Do we look at the constant term?
Yeah, so that'll definitely help there. So what would that allow us to create as far as our list?
X minus 2,
Yeah, so you could have your plus minus 2 factors. What else could you get from this list?
1
Yep, plus minus 1 and 1 left.
plus minus 4.
Yeah, so all those, any x plus or minus these values, you could try. There's also this over here, unfortunately. So whenever you have a coefficient on the leading term as well, those factors also come into play and they form your denominator. That's the rational root theorem side of things, which is something you have to kind of consider when you have a coefficient there as well. So we would create the list from there as well, which would again be plus minus 1, plus minus 2, plus minus 3, and then plus minus 6. The reason why we never had to usually consider that was because if the leading coefficient is 1, then you only got plus minus 1 here. So every time you're dividing by 1, it's the same as if you didn't do anything at all, which is why we usually stick over here. But now that we have this coefficient, we do have to also consider these. So if I were to choose a random pairing, these are your numerators always. These are your denominators always. So one potential pairing could literally be 4 over negative 6, making that and that. Now obviously that simplifies down, but that's just more so to demonstrate. Now the goal is to write those in a way where when you sub it in, it equals 0. That's the guess and check part of things. This is obviously a lot of factors. So what I'm going to do is do a sneaky cheat and then figure out from there where what a factor would be. So okay, 1 over 2 ended up being 1, which would mean minus 1 over 2. Okay, cool. Yeah, that should be fine. So if I were to test the 1 from here and like the minus 2 from here, if I did f of minus a half, I believe that should work out. Okay, 6a, which is going to be minus a half, all cubed, plus 5 minus a half, all squared, minus 12 minus a half, and then plus 4. And with any luck, that'll equal 0 if I've been able to read the answer correctly. Alright, negative a half cubed. That's just going to still make it negative because it's cubed, but then you're going to have 2, 4, 8 on the bottom. And then squaring is going to make it a quarter, so 5 over 4 for that one. And then negative 12 and negative a half is going to make positive 6, and then a positive 4 there. That doesn't look like it'll... Surely that doesn't equal 0. Must have been a positive instead. Oh well, I guess now you'll see what it looks like when it's incorrect. Negative 6 over 8 plus 5 over 4. 6 and 4 is 10. You don't have to go all the way for the answer. If you can clearly see it's not going to equal 0, then just don't bother at this point. It's like you got some fraction as the only negative, and you got a plus 10. It's like good luck trying to make that equal 0. So seems like I misread that slightly. F of a half should be the one that we're looking for here. So if I sub in a half, all that's going to change is it's going to become positive now. So 6, now 1 over 8 from there. This was always going to stay positive because it was squared. Then this is going to go negative because now we're putting a positive a half in this spot. It's going to go negative 6. and the plus 4 obviously is going to stay plus 4. 6 over 8. We'll make this a denominator of 8 so it can condense down, or even just simplify that to 3 over 4. 5 over 4, 6 and 4 is going to make the negative 2 there. 5, 6, 7, 8. 8 over 4 is 2. 2 minus 2, 0. So you can see how if you were testing a bunch of these, starting with plus minus 1, then plus minus 1 over 2s, and then plus minus 2 over 2s, and I mean, you can kind of see that some of them cancel out. Like 2 over 2 is just 1, and so the list isn't as big, I guess, as it seems. But there is a lot of mucking around. So in the interest of time saving, I wanted to cheat a little bit to get one. But anyway, you're looking for an equals 0. Once you have that, does anyone know, now that this equals 0, what that means for our division? Like what that means as a factor?
It's a factor.
Yeah, so it is a factor, correct? But like, what does that actually look like for the linear term, converting this to linear?
Would you mean like it's like x
Yeah, like
minus,
the ax plus b sort of situation.
yeah, you put it like next to like x.
Yeah. Oh yeah, okay. So you could do it's not typical to do like a fractional value for the linear. Usually what you do is you compare it to f of negative b over a, because that is what the factor theorem is. And if f of negative b over a is f of a half, then you just look numerator to denominator, and you would say a equals 2, negative b equals 1, and therefore b equals negative 1. And so from there, the linear, remember a is the coefficient on the x, that's going to be 2x, and the b is going to be negative 1. That also has the exact same solution. You can see if you were to rearrange this for x, you would also get the same thing as if you had just said x minus a half. It's just not super typical to put a fraction in there. So either works, just this is what you'll likely see in an answer, so don't feel like you're going wrong if you're seeing that versus that. Actually, I needed that one. But anyway, that becomes the linear that we know is now a full factor of our polynomial. So we have a linear. The whole point was to find a factor. Why? What does that help us do?
We can like divide the polynomial by the factor to find the rest of the factors.
That's it. Yeah. So the problem that we're having at the beginning here that I probably should have mentioned before was you can't really solve this without factorization and null factor law. It's just not really going to happen all that well. And so part of what we're doing here with factor theorem is to figure, okay, I've figured out that this 2x minus 1 is a factor. So if I were to divide my full polynomial by this, I'll get some quadratic, which I can then work from there. Everything is a factor, and that'll give us my solutions via null factor law. So you would do the polynomial division of this. I'll just copy that. Yeah, I guess we want them in A instead of X, huh? Fair enough. Yeah, these should all have been in terms of A. It's just a bit weird to have A in multiple spots. But okay. So it was 6a cubed plus 5a squared minus 12a, and then it was plus 4. So this is the thing that we're doing a polynomial divide for. Does anyone need me to go through this slow to make sure I'm hitting all this? Well, to make sure you can revise all the steps. Otherwise, I'll kind of just walk through it pretty rapidly. All right. So leading terms divide. So 6a cubed divided by 2a is going to give us 3a squared. Multiply it back through, it's going to give you 6a cubed minus 3a squared. Subtract. It's a 0. 5 minus minus 3, so 5, 6, 7, 8a squared. Drop everything else down. 8a squared divided by 2a is going to be 4a. So you're going to have 8a squared again. And then 4a is negative, so minus 4a. And then cancels, minus 12 minus minus 4 is going to give us minus 8a. Yeah, should be good because the negatives cancel. And then minus 8. Wait, no, sorry, it's 2a. So minus 4 up there after doing that division. You don't even really have to finish it off from here because you know it's a factor, but if you do finish it off, you have the added benefit of error checking to make sure that you actually did it correctly. So if I put everything all the way back through, when I do my final subtraction, I'm really looking for everything to be zeroed out there. Otherwise, I've done something wrong. But anyway, we have the 2a minus 1 from before, and then we have that full quotient, 3a squared plus 4a minus 4. And this is all still equal to 0 because we got it all from this equation, which was equal to 0. Our entire goal was to rewrite this polynomial as a product of terms, because now we can use our null factor law. So, null factor law says what? What can we do from here?
Should we first factorize the quadratic?
Yeah, so factorizing quadratics may or may not have some factors. You probably, I mean, you could mess around with it to see if it's got like a, I mean, it'll have factors, but they may or may not be rational, I guess is what I'm trying to say there. Or even not, actually. Some of them might not even have anything at all. So testing discriminant first could be a good idea, but at that point, if you're already testing discriminant, you might as well finish off the quadratic formula for it. I'll just do a peek in the answer to make sure if it has any integers or not. Yeah, so you could find, I think the book has a interesting incorrect answer here. But anyway, yeah, so it looks like it does have some factors you could find via the cross product approach. So I guess we could revise that a little bit instead of quadratic formula. So cross product approach for factorizing quadratics. Does anyone know what I'm talking about by that?
Chris, is it when you like multiply the A and C terms
Yeah,
and find two numbers that like they multiply to the A and C term, but they add to the B term?
yeah, pretty much, yeah. So we're going to list the factors of our leading term. The only thing that's a slight nuance there is that you don't actually just want the coefficient, you also want the letter that's there as well. It's a little bit different to how you do it for rational root theorem, but pretty close. This could have 4 and -1. It could have 2 and -2. Those are your options there. So as far as how you arrange it, we're just going to try and pick one of these pairs, and the cross multiple of that needs to add up to 4a. So if you don't know what that means, I'll just do it and we'll see. You can see via demonstration. So we're going to have 3a and a, and I think a decent pairing would be, geez, what is a decent pairing? Leave this, putting the 4 there and the -1 there. So I'm using this pair here. You just want to arrange them in a certain order. As for how you perform the cross product, you multiply along the diagonals and you add the results. This is just like product rule if you've seen a lesson on product rule before. Imagine this being like your u dash, v dash situation. 3a times -1 is going to be -3a, and then plus the 4a. That didn't work at all. That was a terrible combination. So that's going to give us a, which is in fact not 4a. So that was a terrible idea.
Chris, could you use 6 and -2?
6 and -2 wouldn't make -4 though.
Oh wait, no, I've done a completely different way to you then.
Oh, sure. Okay. What's the
Um,
idea?
so like I like multiply this is like what like the school teacher showed us.
Okay.
It's like you multiply like the 3 and the -4 because like the A and C terms.
Okay.
And you see how they make -12 when you multiply them?
Yeah, okay.
You then makes us like find like two numbers that like add to +4. So that's like 6 and -2.
Okay.
And then you put them next to like the two pre-existing terms. So you get like 3a squared plus 6a minus 2a minus 4
3a squared, sorry, say again from here.
plus 6a
Plus 6a
minus 2a
minus 2a
minus 4.
minus 4. So
And
that's,
then you factorize using grouping. So you get like you take out 3a from the first two terms,
yeah.
and then you take -2 out of the second two terms.
Uh-huh.
And then since you got like two common brackets, a plus 2 is one of the factors, and then 3a minus 2 is the other factor.
Brilliant. That looks like it works out well. Hang on. Let's see. Is that the answers there? Yeah, you want a plus 2, you want 3a minus 2, and yeah, crushed it. Nice. Nice method there. I haven't actually seen that exactly before. Nice. I like it. Thanks for sharing. And for everyone else, by the way, this 2a minus 1 came from what this was before. So all of what we were just discussing there was how you could potentially factorize that. So to go into a bit more detail here, it looks like what you did was you did the 3 and -4 was the multiply to give the negative, -12 was just because it was this and this multiplied, the 3 and the -4 there. From there, we looked at two numbers that would multiply to give -12 that add to give 4. Did I get that right?
Yeah.
Okay. So it was the the +6 and -2. So we had +6, we had -2. 3 goes here, 6 goes here, -2 goes there, -4 goes there, and then you just, well, as discussed, it was a grouping method there. Okay, fair enough. Yeah, no, well done. I'll revise this myself and see if I can put it in the notes. That way you can have another method of doing this if this cross product, which we didn't really finish, but if this isn't to anyone's liking, we can have a version of this in the notes instead. Cool. Now I've learned something today. But okay, so this was all equal to 0. From here, there's nothing too crazy, right? Null factor law, either this or this or this is equal to 0, and so a being -2, this would be 2 on 3, and this one would be a half. If you do this if you look at the book answer, they actually get this wrong a bit. They said a equals 0 instead of a equals -2 here. It's very clearly a typo, so I wouldn't worry too much about that if you're looking at the book answers. Cool. All right, that's that one.
Chris,
Yo.
just about that last question, like you know how it's taken us like a little bit of time to do this question, like in an actual SAC, like how much time do you think they would allocate us, and like how many marks would that question be worth?
How many marks? Well, I guess the first thing I'll push back on is how long it took. So it took a long time because I'm explaining everything from the beginning. So as soon as you see remainder, you should like immediately just click to it and be, okay, it's remainder theorem, done. Which means you have your linear term, you sub that in, and then from there, you'll be able to create this equation fairly quickly. As for pairings, that can be where things take a fair bit of time. That's why they don't usually ask these kinds of questions to begin with. I reckon they'll give anywhere from like a mark, like potentially a full mark just to figure out what the factor is here, which would give you 1.5 minutes to do all this. ±1 is pretty quick to test, so you can see pretty quickly it's not going to be one of those. The next thing you should be testing after that is ±1/2 anyway, just because you should be doing it in order of easiest to hardest fractions. So I can imagine 1 mark for getting this equation, 1 mark for finding your factor, and then this polynomial division, I mean, I blitzed through that. It was maybe sub 1 minute, and that was with me talking out loud on it. Now, obviously, I'm practiced, but you should also be practiced if you're doing the test. And then this factor stuff here, I wouldn't even bother looking for. I would just go straight for quadratic formula because, yeah, it might take a little bit longer if you don't know what the factors are, but it should be pretty bulletproof to get there. So all in all, what did I even say? It was 1 mark for finding the remainder theorem thing, 1 for this, 1 for this, and then 1 for answer. So what's that, 4 in total? That'd be, yeah, what I think, 4 in total, which would give you a lot of time if it's 1.5 marks per minute. Fair enough. That all being said, that's kind of why they don't really ask these questions. They don't feel like giving too many marks away for one question, which is why you usually don't get remainder or factor theorem stuff in an exam at least. Maybe in a SAC because, well, SACs are usually pretty targeted. But okay, cool. We may or may not fly through a few questions a bit more speedier this time. So question 2, express x squared plus 8x plus 9 in the form x plus a all squared plus b. So does anyone immediately see the relationship between those two, how you might go from one to the other?
Complete the square.
Complete the square, absolutely. So complete the square, I mean, as long as you're familiar with your complete the square formula, or you could do the method version where you halve the b term and then convert, either would work fine. If anyone wants me to actually do that, let me know. Otherwise, we'll just move on to the next question, which would be, after we have our completed square, how do we know where the minimum on our graph is? And to make that a bit easier, I'm just going to make up a completed square, ideally legible this time. And then we can use that for our discussion.
Chris, do you just use the constant term outside of the brackets because that's your y translation?
Yeah, correct. So because it's a positive quadratic, it's always going to look something like an upright parabola. And so the vertical translation will always be the absolute lowest y point on that, hence the minimum. So in the random example I gave, the minimum would be 4 if you had that as your completed square. Okay, define the range. Yeah. Anyone know how you define a range of a linear? Not, does anyone know what or remember what the range is of a function?
It's the restrictions, the vertical restrictions.
Yeah, so the absolute max and absolute minimum y value. So we're given a restriction on our domain here. That's what the function notation says. We're from -3 to 5 as far as our linear goes. What could we then therefore do to figure out the y restrictions? Even if you don't know the actual numbers, what might we start doing?
We sub it into the function.
Yeah. So basic little hack here. If you know your function is strictly increasing or decreasing, so like 6 minus x just means basically that, right? Y-intercept is 6 and it points downwards. If you know the function isn't going to go back on itself ever, like a quadratic does, then you can find the range by just looking at the absolute endpoints of it. It's a little bit harder for quadratics because you can't just look at the endpoints here because you miss this spot. So looking at your function, knowing that it's a strictly increasing or decreasing function, you know to just look at the ends. Whereas if you did have a turning point or something where it goes back on itself a little bit, then it's a bit more complicated to find. But there should be enough context clues in that. So yeah, in this case, our endpoints are -3 and 5 respectively. So this would be -3, this would be +5. You sub those in to your function 6 minus x, that'll give you the y values at those spots. Okay, question 4 is more transformations. We kind of already did that. Question 5 is a little bit different transformations. I can look at that if you want, so let me know if anyone wants to do question 5. Otherwise, I'm curious to see question 6. Yeah, okay, cool. Question 6 it is then. So, we have I almost don't want to say it. We have a linear divided by a linear, and we want to rewrite it into a hyperbola, essentially. Does anyone remember? I mean, there's a bunch of ways you could do this. Anyone have any thoughts? And I'll give a moment to think about it, of how we can get from here to here. There's actually going to be a technique we've already used as of today that can be used to handle this. Okay, so the hack here always is that if you have this linear divided by linear situation, yes, you could do algebra to get it to look like this, but a polynomial division will also work perfectly fine as well. What you might not notice about the hyperbola, or at least until I've mentioned it again, is that you've basically got a quotient section, which is the perfectly divisible part, and you've got the remainder section, which is your remainder after division by x plus 1. So this actually just is the result after dividing a linear by a linear. You get something that looks like a hyperbola every time, as far as the polynomial division goes. So if I briefly go through that, it'll be a very quick one. X plus 1 divided by 4x minus 7. 4x divided by x is going to give us 4. 4x plus 4, do your subtraction. It's going to cancel down here. And then minus 7 minus 4, minus 11. So that's obviously your remainder there. So when we think about our quotient, it's 4. Our remainder being negative 11, you've got to divide that by x plus 1. That is a hyperbola. You have y equals your function 4 minus the 11 over x plus 1. So in this case, your a value would be 11 and your b value would be 4. So that's a quick hack that will always work there. You could do it algebraically instead. That kind of requires a bit more like thinking as to how you'd rearrange it. Honestly, just you're going to have to get good at your polynomial division anyway. You might as well just use this version. I'll show it as brief as I can as far as how you would do algebra, just so you have all the options available, which is you would start with your linear, and your whole goal is to basically separate this into a you want to get a whole number out of this at the end. So you want to split this fraction up into a way where the terms divide together perfectly, and then there's a part that's left over. And so from here, basically, we want to have some x plus 1 in our numerator up here, which would mean, what do we mean? Yeah, okay. So if we were to do that, we could do 4x plus 4 and then minus something to make it look like minus 7 at the end. So if I add 4 to this, I've got to subtract 4 from here, which means minus 11 all over x plus 1. Basically, it's introducing terms or splitting this sort of up so that when you eventually split your fraction up, so 4x plus 4 over x plus 1 minus 11 over x plus 1, you can see if you took a common factor of 4 out the front from here, you'd have x plus 1 over x plus 1. Those would cancel. This would still drop down. And you're left with 4 minus 11 over x plus 1, just like we discussed or created from earlier. So this is why I'm not recommending you do it this way. I'm just showing that you could do it this way if you wanted to strategically introduce terms, because this and that are the same. Those are both -7. We're just rewriting it in a way where you can rearrange a little bit there. So all that to say, don't do that unless you really like your algebra. Stick to polynomial division. Okay, that's that. Then from there, points of intersection, asymptotes. Yeah, sure, we'll touch on that. So we now have our hyperbola. How do we find the axes intercepts of a hyperbola?
We just sub in like y is equal to 0 and x is equal to 0 to find intersections of the axes.
Yeah, it's a bit of a trick question. Just any axes intercepts will always be y equals 0, x equals 0. Doesn't matter if I say hyperbola, truncus, anything, it'll always be that. And the last part of that question is the asymptotes. So a little bit different. Now you've actually got to consider the actual function now. How do we know the asymptotes of our hyperbola?
You can just observe that by looking at the x and y translations.
Yeah, correct. So the key nuance is that your y translation gives you your x asymptote, and your x translation gives you your y asymptote, which might feel a bit weird, but think about it as, well, how else would you think about it? The vertical translation, I'll start with the actual hyperbola. So your basic hyperbola looks like that. The reason why it has a vertical asymptote at all is because of a divide by 0 error. So basically, whatever causes this to go to 0 will give you a vertical asymptote. That's why this is setting your oh, hang on, what am I saying? Did I get this back to front? I did. I'm stupid. Whoops. Never mind me. I got that back to front. It is in fact y equals 4 because I just shifted up, and then x equals, yeah, don't mind me. That was just a brain fart there. Sorry. Okay. But yeah, just looking based on the graph, vertical gives y and horizontal gives x. Yeah, I don't know why I thought that was backwards. Anyway, question 7. We have a bunch of vertices on a triangle, midpoints, and therefore coordinates of m and n. Huh, that's kind of interesting. All right, so we can have a proper discussion about it. I'll just draw these on an axis. And in the meantime, while I'm drawing those, maybe have a think about what the question's asking and how you might go about it. Okay, so that's the plot of the points there. It then says M and N are the midpoints of AB and AC, respectively. So this would be considered AB, and so M should be the midpoint there. So my drawing isn't to scale. It may or may not be left or right of the y-axis. So just keep that one in mind. And then N would be our AC. So based on the scale I've drawn here, that would be N. These are supposed to be midpoints, so equidistant here and here, and equidistant between A and B as well. So if you wanted to find the coordinates of m and n, what do you think we might do?
You just add you want to use a midpoint formula on the two given points.
Absolutely. Yeah, midpoint formulas. Do you remember what the midpoint formula is?
X1 plus x2 over 2,
Mhm.
comma y1 plus y2 over 2.
Absolutely. Yeah. So it can be helpful to define, like, point A is x1, x2, and point C can be, oh, sorry, point A can be x1, y1, and point C can be x2, y2, and then that can allow you to make sure you don't get these back to front. It's kind of hard to get them back to front because there's nothing in a denominator really. It's just, here's the x on the first, here's the x on the second. It just sort of stops you from, I mean, even I said it out loud accidentally. I said this is x1, x2, which is obviously not. And so, like, literally writing on your page, A is going to be x1, y1. That can be kind of effective as far as making sure you put things in the right spots. But otherwise, yeah, just chuck it into these spots. So if I were to do it just for the AC one specifically, it would be, okay, A was -2, so you'd have -2. It was C, which is 5, so you'd put that there. I don't know why I put a comma there. And then Y1 is from A, so 1. And then Y2 is from C, so 7. And this would be the point N specifically. So 5, 4, 3 over 2, and then 8 over 2, so 4. That would be the point N there, which should make enough sense based on the graph, although obviously mine's out of scale because, well, I freehanded it after all. But at least it was in roughly the right quadrant there. It's more so just so you can see what's going on rather than it being completely accurate. Like, I wouldn't be surprised if you solved this, it was like somewhere over here instead. But yeah. Yeah, you would just do it for the exact same thing for the other point. Now, the next question is to prove that MN is parallel to BC. So MN would be this line connecting here. Oh wow, that actually almost looks parallel. Look at that. I actually did draw it kind of not bad. Prove that MN is parallel to BC. For that, we're going to need, well, I'll shut up a bit there and let you have a think.
The gradients of the two line segments.
Yeah, gradients of the two line segments. So how do we find gradients of line segments?
Y2 minus y1 over x2 minus x1.
Yeah,
Or
correct.
what we say rise over run.
Yeah, all that's fine. Yeah, so obviously for that you would need both m and n for that. You do the gradient of those 2 points, gradient of these 2 points. Are they the same? Yes. In which case they will be, well, parallel, because parallel lines have same gradient. If anyone wants to see the arithmetic for that, let me know. Otherwise, I shall move on to the next question, given that we have, like, what, 6 or so minutes left? Okay. 8, we've already done a lot on that. That's just substitution, so we'll skip that. That's kind of whatever. Oh yeah, simultaneous is kind of maybe hard. Solving simultaneous equations, question 11. So we have x plus 5, say again, we have x plus y equals 5, and then we actually have a circle equation going on there. So even though circles aren't necessarily in a study design, that doesn't mean you can't actually work with them. The fact that this is a circle actually doesn't have anything to do with how you solve it at all. So I'll give a moment to think about what you might do here. And yeah, we'll take it from there.
Chris, in a test, are we allowed to just solve by observation or no?
Guess it depends on how many marks, because you'll get a mark for answer no matter what. If it's a 2 marker, you're going to have to show some work. So really it's just how many marks are there would be the correct answer for how to justify that, yeah. So by observation, are you seeing, what would you be seeing? Yeah, actually, what would you be seeing?
For the simultaneous?
Is it 4 and 1? No,
No, 2 and 3.
2 and 3, you spotted it. 2 squared is 4, 3 oh, sorry, no, it's not even 2 squared, it's 2 plus 1. Yeah, okay. Does that, is that final answer x is 2, y is 3, or vice versa? Because how you write the final answer actually matters here. Oh yeah, it looks like 2 and 3 are good. It's just what do you actually write?
They're interchangeable.
Yeah, they're interchangeable. And so how do you actually write final answer?
Yeah, I don't know about that.
Yeah. So it's right. So 2 and 3 are correct. And for everyone else, we will go through how to actually solve it instead of by observation. So you're going to have two things. You're going to have the x equals 3 or the x equals 2. And you're going to have the y equals 2 or the y equals 3. These would be your two sort of pairs of answers there. As for how you actually express it, you would say either x equals 3, comma, y equals 2. Then you would say or use the same order, or x equals 2, y equals 3. This is accepted by VCAA. This was literally their, it was a very similar question where it could be interchangeable. That was what they did for a very similar sort of thing, where you give the first pairing with a comma, then an or, the second pairing with a comma. Okay, so that's how you express your answer. As far as how you do this without observation, you've got really, I mean, you do have elimination method, but by God, will it take a lot of effort to make that work. Better off just using substitution method for that. And the easiest one to rearrange would be the x plus y equals 5. You just want to get one of these variables on its own. Then from there, that'll be your substitution. We have the equation, which is x plus 1 all squared plus y, which is now 5 minus x, plus 1 all squared equals 25. This is now an equation with just x's in it. From there, you would solve it like you would for any other quadratic. You expand this out, you expand this one out, condense it down, solve a quadratic using either quadratic formula, factorization, all the methods that you have there. Okay, cool. So this is a really good place to be if you've already, and you have at this point if you've been in these classes, if you're at the point where you've studied pretty much everything in functions and relations. So if there's no like major holes in your understanding of things, this is a great place to start working, which would be this chapter 8 in Cambridge. Jacaranda also has them as well. Has these review chapters at the end of their, wait, actually I don't even know if Jacaranda has a full review chapter or everything. It has it chapter by chapter, but not necessarily. I'll have to check. But anyway, this has got some tech free, it's got some multis, it's got some external responses, and then there'd also be the practice acts that I have in the school group in the classroom tab. So that'll be the functions and relations sacks. It'll basically be what we did here 5 times, but it's at an exact it'll be to the exam standard. So it'll be 60 minutes total for the tech freeze, there's 5 of them, and it'll be 2 hours 15 for the tech active, which there are also 5 of them there. So if you're at the stage where there's no real major holes in your understanding, this will be where to go. All right, I'll leave you guys to it. Take care.